Sorry. Okay, we're going to miss a little bit of this on the video, but I think we're now recording. Yeah, we are. This has happened to me before, so anyway. Suppose that a recent article stated that the mean time spent in jail by a first-time convicted burglar is 2.5 years. A study was then done to see if the mean time has increased in the new century. A random sample of 26 first-time convicted burglars in a recent year was picked. The mean length of time in jail from the survey was 3 years, with a standard deviation of 1.8 years. Suppose that it is somehow known that the population standard deviation is 1.5. Okay, if you were conducting a hypothesis test to determine if the mean length of jail time has increased, what would the null hypothesis and the alternative hypothesis be, and assume that the distribution is normal. Okay, all right. So in this case, our null hypothesis is based on historical data, and let's say this article states that it was 2.5 years. Okay, sorry. So our alternative hypothesis is that mu is 2.5. Okay, so if we were to test this hypothesis, it would simply be that it's 2.5 based on known or assumed, an assumed value, and the article claims that it was 2.5. So our null hypothesis is that mu is 2.5. Now, a study was done here using the sample of n equal to 26, and the claim is that the mean time has actually increased. Okay, so we'd have to reflect that in our alternative hypothesis and state that mu is greater than 2.5. Okay, remember the claim is really the alternative hypothesis. Okay, so there we have this null h naught mu is 2.5 against the alternative that mu is greater than 2.5, and this data here that we see here shows us that the mean was 3 years. Okay, so is that a significant value? Well, we'd have to do an hypothesis test, but these would be the hypotheses that we would be testing. Okay. All right. Now, a sleeping bag is tested to withstand temperatures of negative 15 degrees Fahrenheit. You think the bag cannot stand temperatures that low. All right. So the type 1 error is the probability that you reject the null hypothesis when it's true. So in fact, you would be stating that the bag cannot withstand negative 15 degrees Fahrenheit, okay? But you don't believe that. You think it can withstand. So that's the type 1 error, okay? That would be assuming that the null hypothesis would be mu, the mean temperature is negative 15 degrees Fahrenheit, against the alternative that it's greater than negative 15 degrees Fahrenheit, right? That's your assumption going in. And the type 1 error would be rejecting that null hypothesis when it's true. Okay. The type 1 error is accepting the null hypothesis when it's false. So you would conclude that the bag cannot withstand, all right, negative 15 degrees. The alternative is that it's greater than negative 15. But you conclude H naught, that is that it is 15, negative 15 degrees, okay? So that you would be committing the type 2 error, accepting the null when in fact it's false, okay? All right. Let me just check something here. Okay, so someone's in the waiting room. No, we don't have, don't think we have anybody in the waiting room. Okay. Will this Zoom be posted on Canvas? Yes. And will you have 2 chances on the test like we did in the practice test? Yes. Okay. All right. Okay, number 9. We're almost up to 2 o'clock. You are performing a hypothesis test of a single population using a student's T. The data are not from a simple random sample. Okay. There's some mechanism in the sampling that doesn't allow a random sample. Okay. Can you accurately perform the hypothesis test? And the correct answer is no. Remember that all of our assumptions in hypothesis testing is that the data is collected independently and randomly. Okay. Sometimes in textbooks that's abbreviated as IID, independent and identically distributed. Okay. So the random sample, you know, if it weren't random, it might affect the fact that you're assuming identical distributions for each of the sample pieces. Okay. All right. Suppose that a recent article stated that the mean time spent in jail, okay, is by a first-time convicted burglar is 2.5 years. A study was then done to see if the mean time is increased in the new century. A random sample of 27 first-time convicted burglars in a recent year was picked. The mean length of time in jail from the survey was 4 years with a standard deviation of 1.9. Okay. Suppose that it is somehow known that the population standard deviation is 1.4. Conduct a hypothesis test to determine if the mean length of jail time has increased. Assume the distribution of the jail times is approximately normal. Okay, so in this problem, the sample mean here is given to be 4 hours. So that's our sample mean, 4. Okay. And our standard deviation is assumed to be known up here. And so we would specify sigma then as that known standard deviation, and that's given to be 1.4, right? And then the sample standard deviation we're told was 1.9, right? And our sample size n is 27, okay? So with the information given to you in the problem, you would see, you would then recognize that all of these values are given to you up in the body of the problem. And then you could go forward with your test. Okay. All right. Draw the general graph of a left tail test. Well, you have 4 choices here, and the correct choice is this graph here, right? Because it's a left tail test. So your test statistic typically falls to the left of 0. And we know that the left tail test has a less than in the alternative, so the p-value would be measured using the left tail. Okay, all right. So there you have the correct graph. All right. Now, if the alternative has a not equals symbol, you know to use which type of test. Okay, well, the not equals symbol means that it's a two-tail test. Okay, your rejection region will be a left tail and a right tail. Okay, so it's a two-tail test. Indicate which of the following choices best identifies the hypothesis test. Okay, let's read the problem here. Looks like there's a little bit of typesetting errors going on here. Let's see if we can decipher this. The known standard deviation in salary for all mid-level professionals in the financial industry is 11,000. Company A and Company B are in the financial industry. Suppose samples are taken of mid-level professionals from Company A and from Company B. Okay. All right. The sample mean salary for mid-level professionals in Company A is 80,000. The sample mean salary for mid-level professionals in Company B is $96,000. Company A and Company B management want to know if their mid-level professionals are paid differently on average. Okay, so indicate which of the following choices best identifies the hypothesis test. Well, we see that Company A and Company B are basically maybe identically distributed, but they're certainly independent. Okay, so they have independent group means. And the known standard deviation is given here. Okay, that's the first sentence in the statement of the problem. The known standard deviation in salary is 11,000. So the correct choice is this second choice here. Independent means population standard deviations or variance is known. Okay. Indicate which of the following choices best identifies the hypothesis test. A new medicine is said to help improve sleep. 8 subjects are picked at random and given the medicine. The means of the hours slept for each person were recorded before starting the medication and after. Okay, so really what we're doing is comparing per individual in the study, the amount of sleep before and the amount of sleep after the treatment was given. And so we can match pairs, can't we? All right. So the 2 sample problem becomes a 1 sample problem by taking differences, let's say. All right. And so we choose the second option here, matched or paired samples. All right. That's not always the case. Sometimes you can't pair the samples up like this, but it's pretty obvious when you have a situation where they are matched pairs. Okay. And you probably did some of those in your homework already. Okay, the next problem, the US Center for Disease Control reports that the mean life expectancy was 47.6 years for whites born in 1900 and 33 years for non-whites. Suppose that you randomly survey death records for people born in 1900 in a certain county. Of the 124 whites, the mean lifespan was 45.3 years with a standard deviation of 12.7 years. Of the 82 non-whites, the mean lifespan was 34.1 years with a standard deviation of 15.6. Conduct a hypothesis test to see if the mean lifespans in the county were the same for whites and non-whites. Okay. Now, in this situation, we need to calculate a test statistic, all right, or a t statistic. Okay. So the Z is typically used when the sample sizes are large and the standard deviation is known. Okay. If the sample size were small and you didn't know the standard deviation, you typically use the t. All right. And the corollary to that fact is that if the sample size is large and you estimate sigma using S, you can still use the t. All right. And some textbooks say you can also use the Z, even if the standard deviation is unknown. All right. So in this problem here, we have the two choices, Z or T. And since the standard deviations are estimated, let's go with the T distribution. All right. And okay. And then here, calculate the T statistic. All right. So let's go to StatCrunch over here. And we'll calculate the t-stat. Okay, let's see, I think I've already got it here. No, yeah, here it is right here. Okay, so how do we calculate the two sample t-test? All right, so let's look at that. You know that your testing falls under the stat superfunction here. And since we've surmised that we have a t-test, we go to t-stats. We've got the two sample with summary, okay? And in our summary, we would fill the action window here with the mean, the standard deviation of the sample size of the statistics for the white sample and for the non-white sample. I'm not going to do that. Okay, I'll show you the results again. And then let's see. And then the other thing we have to be careful about is the orientation of the inequality sign in the alternative hypothesis. Okay. And since our claim here is that they're the same, okay, then notice our alternative would be not equals here, okay? And if you set that up, let me go back to our results, okay? I'm sorry, having a little trouble here getting to my, okay, so let's go back to our results here. Okay, and so here's our alternative against the null, that they're equal versus they're not equal. That conforms to the wording in the problem, and StatCrunch will calculate the t-stat for us, okay? And we get 5.4209927 in StatCrunch. And remember the t-stat here is rounded to 3. So we have to take this value here in StatCrunch and round it to 3 places. And you can see that it's going to be 5.421. Okay, so that's the correct answer, 5.421. And here's the p-value. And the p-value is less than 1/10,000th. And we can effectively say that it's 0. It's not quite 0, but it's certainly close to 0. So the correct answer here would be 0. All right. Okay. Any questions about this? I did a shortcut here. I didn't actually fill in the action window with the data here, but I am showing you the results of doing that. Okay, do you have any questions about this one? Any questions? Okay. All right. Okay, so there we have the t-test for the 2 samples. Okay. Two metal alloys are being considered as material for ball bearings. The mean melting point of the 2 alloys is to be compared. 15 pieces of each metal are being tested. Both populations have normal distributions. And here you have a table with the mean melting temperature in Fahrenheit and the population standard deviation. Okay, so the mean melting temperature in degrees Fahrenheit for alloy gamma is 800 degrees Fahrenheit, and alloy zeta is 900, and the population standard deviations are given here. Okay. All right. Now, the comparison here, notice the comparison is neutral in the sense that we're not saying that the melting point of one alloy is different than the other alloy. We're not saying that, okay? We're just testing to see whether, in fact, they're not equal, right? So the correct answer would be this graph here, because that alternative hypothesis would give us a two-tail test, and the shaded area represents 1/2 the p-value. So this graph here is the correct graph. Okay. All right, let's read the next problem here. 2 types of phone operating systems are being tested to determine if there is a difference in proportions of system failures, crashes. 15 out of a random sample of 150 phones with OS 1 had system failures within the first 8 hours of operation, whereas 10 out of another random sample of 150 phones with OS 2 had system failures within the first 8 hours of operation. And we might conclude that OS 2 is more stable than OS 1, okay? So let's go into StatCrunch, and we're going to do a test of two proportions, right? And here is the test here, okay? Again, I've left out the action window, and what I'm showing you are the results of what you would obtain once you filled in your action window with the successes and the number of observations for each of these two samples. And notice that the counts are given here, right? So here is OS1, 15 failures out of the 150, OS2, 10 failures out of the 150, and you calculate your z-stat, and there it is right here, okay? And again, round your answer to 4 decimal places, and your rounding would give you 1.0. I'm sorry, I'm looking at the wrong number. Here it is. Your p-value is 0.1481, okay? And I presume that you're all comfortable with deriving these results in StatCrunch. That part of it I haven't shown you. But again, you would go to your stats, your proportions calculator, your proportions test up here. Okay, it's a 2 sample. You have the summary. You get your action window, fill in 15 out of 150, 10 out of 150, and now derive your results. Okay. Any questions about this problem? A test of 2 proportions. Okay. All right, let's go to this one. In a recent survey, in a recent census, 3% of the US population reported being of 2 or more races. However, the percent varies tremendously from state to state. Suppose that 2 random surveys are conducted. In the first random survey, out of 1,000 North Dakotans, only 9 people reported being of 2 or more races. In the second random survey, out of 500 Nevadans, 17 people reported being of 2 or more races. Conduct a hypothesis test to determine if the population percents are the same, or if the percent for Nevada is statistically higher than for North Dakota. And the question is, which distribution would you use for the hypothesis test? Okay. Well, here you have 2 choices, students T or the normal. All right, now since this is proportions, your test would be the proportions test, which is based on the normal distribution. Okay, remember the proportions are modeled using binomial, and when n is large, as they usually are in these proportion tests, then in fact you can use the normal approximation to the binomial. Okay. All right. If the number of degrees of freedom for a chi-square distribution is 64, what is the population mean and standard deviation? All right. Round your answers to 4 decimal places. If you don't remember what the mean and the variance of the chi-square distribution are, you can look them up by checking your book, your eText link, and it takes you right to the information that you need. Okay. For the chi-square distribution, the population mean, mu, is just the number of degrees of freedom. And the population standard deviation is sigma, equal to the square root of 2 times the degrees of freedom. All right. So with those facts in mind, now we can answer these questions. We're told that the DF for this chi-square distribution is 64, so the mean is 64. Now, the population standard deviation is the square root of 2 times 64, which is 8 times the square root of 2. And if you put that into the calculator and round it to 4 places, you'll get 11.3137. Okay. So this indicates how handy this link is if you need a quick refresh from the text material. Okay. And this problem says the cumulative number of AIDS cases reported for a county is broken down by ethnicity as in the table below. Okay, so here is a table listing ethnicity down the rows, and the second column is the number of cases here. Okay, and the total of all of these cases is 4,075, and the 4 ethnic groups are white, Hispanic, Black, African American, Asian, Pacific Islander. The percentage of each ethnic group in the county is as in the following table. So here are the county statistics here, all right? And here it says that white is 42.7%, okay? And notice that 42.7% of the total in the county, 4,075, is 1,096.18. Okay, put that into your calculators, calculate your percentages there. Okay. And let me just show you what we get here. You may be doing this on your own calculators. Let me go to the calculator again here. Okay, hold on. Let me. Okay, so here's the calculator. Can you all see this? Okay. All right. So if we multiply 42.7% times the total, we'll get the 1,740. Okay. And then 26.9% of 4,075. Do that on your calculator, and you get 1,096.175, and so on. Okay, so those are your percentages just by using your calculator, all right? And okay. Okay, so you can see that you can easily calculate these percentages here by multiplying the given percentages by the total 4,075. Okay. The next problem states, Transit Railroads is interested in the relationship between travel distance and the ticket class purchased. A random sample of 200 passengers is taken. The table below shows the results. The railroad wants to know if a passenger's choice in ticket class is independent of the distance they must travel. Okay, all right. So let's look at the contingency table here, where the row labels are the traveling distance and the column labels are third, second, and first class frequencies, okay? And in a test for independence, we have these two attributes, and the null hypothesis is always that we're stating that the two attributes are independent against the alternative that they're not independent, okay? So this second choice here is the correct set of hypotheses. The ticket class chosen is independent of the traveling distance against the alternative, the ticket class chosen is dependent on the traveling distance, okay? All right. And in this problem, let's actually do the test for independence of traveling distance versus the type of ticket the traveler purchases. We'll test at the 5% level that these two attributes are independent, okay? All right. So let's go ahead and do the calculation in StatCrunch here. So let me, I think I have the results here. Okay, here's our contingency table. Now, remember how you derive the contingency table here in StatCrunch. Let me show you that. Okay. All right. Now, let's hide this again. And then for the contingency table, that's listed under the applets superfunction here. So we come down and choose the contingency table option. And then you name your row labels here and your column labels. You can enter up to 5 comma delimited values. Okay, so be careful how you enter your labels here, and just separate them using a comma, okay? And hit compute, and when you do that, you'll get your results. All right, and so here it shows you your contingency table, and when you hit compute, you'll get a blank contingency table here. You've already specified what the labels are. Okay, this is how I specified them. And then I filled in the data based on our given problem data up here. Notice that all I did was replicate this data table now here in my StatCrunch spreadsheet. Then I hit compute. And when you hit compute, you get the test statistic and the p-value here, okay? Now, the p-value is 0.0435. Remember how we make a decision in a chi-square test, or in all of the tests that we've considered here. If the p-value is low, H0 is a no-go. That is, if p-value is smaller than alpha, in this case, alpha is 5%. So notice that the p-value is smaller than 5%, so we would reject the null hypothesis, okay? It's close, isn't it? I mean, 0.0435 is not that far away from 0.05, but in the machinery of hypothesis testing, if we use the p-value, then our decision is strictly if p-value is smaller than alpha, then we reject the null hypothesis, okay? All right. And what's the other way of making a decision Well, you could calculate the critical value for the chi-square test at level 0.05. That'll give you some value here on the x-axis, and then you compare your test statistic with the critical value, and there it turns out that the critical value will be inside the acceptance region. That is, it'll be to the left of your calculated critical value here, okay? So the critical value is going to be higher than 16, and so sorry, it's going to be to the left, isn't it? Okay, it's going to be less than 15.922764. Okay. No, what I said was correct the first time. Critical value, yes, the critical value will be slightly to the left of 15.92. 15.922764 falls to the right of your critical value, putting you just inside the critical region here. Okay? All right, and that would tell us we reject. Okay. All right, we've got a few more here. I know we're going into our second hour now. All right. An article in the New England Journal of Medicine discussed a study on smokers in California and Hawaii. In one part of the report, the self-reported ethnicity and smoking levels per day were given. Now, the rest of the verbiage here describes the statistical samples by ethnicity here, okay? And notice that the 4 ethnicities are African American, Native Hawaiian. Actually, there are 5, aren't there? African American, Native Hawaiian, Latino, Japanese Americans, and white. And then the row labels are the smoking level per day, 1 to 10 cigarettes, 11 to 20, and so on. Okay? All right. What is the formula for calculating the degrees of freedom for the chi-square test here? Okay. This is a chi-square test, isn't it? Because we have our contingency table here, and probably the study would like to make a conclusion. Is there a dependence on ethnic group and smoking? All right, or are they independent? Okay, so in this case, we're asking for the degrees of freedom of the contingency table, which in turn would give us the degrees of freedom for the chi-square. And the formula is R-1 times C-1. Let's see what the ebook, if that tells us. Okay. All right. It's not obvious from the book here where that fact is, but we know that to be the case. And let's count up the rows. We have 1, 2, 3, 4 rows here. So R-1 would be 3. We have the 5 ethnic groups. So C is 5 and C-1 is 4. So 3 times 4 gives us the value 12. Okay? Okay. Right. Next problem, a math teacher wants to see if 2 of her classes have the same distribution of test scores. What are the null and alternative hypotheses for this situation? Okay. And notice that in the second choice, you have basically a test for homogeneity. Homogeneity tests whether 2 distributions are the same. So in fact, the second pair of hypotheses is the correct pair, okay? The two distributions are the same versus they're not the same. And again, a contingency table using chi-square would give you a test statistic for this test. Okay. All right. This problem says a vacation resort rents scuba equipment to certified divers. The resort charges an upfront fee of $25 and another fee of $12.50 an hour. Okay, so there's a going in fee and there's a fee based on the time of usage of the scuba equipment. Find the equation that expresses the total fee in terms of the number of hours the equipment is rented. Okay, well, let's take a look up here. We've got a linear function, don't we, where we're adding 25, that would be the y-intercept. So y is equal to the y-intercept plus the slope times x. And the slope is 12.5. That's the hourly charge, okay? So the hours are the independent variable. And if the scuba diver goes out for 4 hours, she would be charged $12.50 times 4, which would be $50, plus the $25 fee going in, okay? So this would be the correct equation for expressing the resort charges for the scuba equipment. Okay. And similarly in this problem, a credit card company charges $10 when payment is late and $5 a day each day the payment remains unpaid. Again, this is a linear function. The y-intercept is 10. Okay. The slope is 5, and so our equation would be 10 plus 5 times the number of days late. Okay, simple linear equation there. A random sample of 10 professional athletes produced the following data, where X is the number of endorsements the player has, and Y is the amount of money made in millions of dollars. Okay. All right, very lucrative to be a professional athlete. All right, so use the regression to find the equation line of best fit. Okay, so let's go to StatCrunch, and I've listed the data here in columns X and Y. Okay, all right. So let's just inspect the data. We have a sample of size 10, and the predictor variable is the number of endorsements, and the response, the Y variable, is simply the amount of money made in millions of dollars. Okay, so let's go to the regression, simple linear regression. And okay, and there, let's see. This is not the correct results. Okay, let me show you the correct results here. Okay, here we go. This is the correct situation here. I'll tell you why the first one was incorrect. I believe that when I came down to 6, when X is 6, I typed in a 1. Okay, and when I saw this, the first result, then I rescanned the data, and actually 14 is the Y pair, is the Y value for when X is 6 here. Okay, and here are the results for that regression. And let's see, round your answers to 3 decimal places. So y here would be 2.1956. Okay, the y-intercept would be 2.196 if you round to 3 places, and the slope of the line would be 1.795. Okay, and those are the correct answers. All right. Okay, and number 28. Okay. What happens when you have 2 data values in your scatter plot? Okay, R is 1 because linear regression will fit a straight line passing through those 2 points, and that straight line fits the data perfectly, right? Okay, so we can't really use just the 2 points. So here we would say that the data are not significant. We don't get any information with a sample size of 2. Okay. 2 is considered to be too small. All right, and even as few as 3, 4, 5, we might have a little bit of doubt in fitting a line to such a small sample size. We could do it, but we'd have to be careful in interpreting the results. Certainly when n is 2, that's too few. Okay. Now, remember that 2 points determine a line in the plane, and that line can be, it could have negative slope. If it has negative slope, then the correlation coefficient of those 2 points would be -1. And if it's not negative, it would be equal to 1. Okay, unless they were the same point, then the slope is 0, and we don't get any results there. So R will always be either 1 or -1 if you have 2 points in the data set. Okay. Okay, we're getting down to the end here. A landscaping company is hired to mow the grass for several large properties. The total area of the properties combined is 1,350 acres. The rate at which one person can mow is as follows. And notice the caret over the Y. This indicates that it's been fit. The X and Y data have been fit with a straight line whose slope and y-intercept are given here. The y-intercept is 1,350. That's the size of the area. And the slope is -1.5. Okay. And X is the number of hours. Okay. And Y hat represents the number of acres left to mow. Okay, so how many acres will be left to mow after 46 hours of work? And in that case, all we have to do is plug in a value of X equal to 46 in our regression equation. And just for fun, let me show you the calculator here. All right, let me switch the zoom to this calculator here. Okay, and here's our calculation right on the calculator. 1,350 minus the slope 1.5 times the predictor variable of 46, and that gives us a value of 1281. Okay, so there you see the calculation done right on your calculator. Let me go back to the test now. We'll finish this up. Okay. So the correct answer is 1281 that you get just by plugging in your 46 into your regression equation and getting a y hat value of 1281. Okay. And then the last problem. The table below contains real data for the first 2 decades of AIDS reporting. Graph year, here's the year, and we're only going to use the years after 1980. Okay, so we'll use these 22 consecutive years, 1981 through 2002. So we'll leave out the top line here in our table. So we'll graph year versus number of AIDS cases diagnosed. Do not include the pre-1981 data. Perform linear regression, and we'll write the equation based on our work in StatCrunch, and then we can fill in the blanks here. Okay, so let's go to StatCrunch. Let me bring up the results. Okay, here's the scatter plot. And notice that the number of diagnosed cases rose steadily, sort of in a linear fashion, until the year about 1993, and then it started to go down. So really looks like there are 2 things going on here. Better treatments maybe happened in the middle 90s, and the number of cases diagnosed goes down, okay? And then it flattens out a little bit. No new breakthroughs have been discovered, possibly. So there's your regression equation, your scatter plot, and then the other part of your results here are the line, okay, as a line here given to you as y plus mb, y plus mx, and you can read out the slope here, -3448225. Round the slope to whole numbers. 1750, the correlation coefficient, and so on, okay? And the sample size. So that concludes our problem solving. And I want to make a few comments before we leave, okay? And I'll give you these instructions when I post the exam. Tomorrow, you'll have tomorrow through Saturday to complete your final exam. Okay, so the only other requirement that I'm going to ask you to submit to me via campus or Canvas email would be a .scs file based on your StatCrunch session. And so let's go to StatCrunch now. Here's our StatCrunch spreadsheet. Oh, wait. Okay. And in StatCrunch, you can save your session by downloading it. So I've done a lot of calculations in StatCrunch. I have a whole list of results that I've done in calculating and finishing my test. And now I can save that session by simply downloading it. So this will save the .scs file, and I'll be able to open that file and then look at your calculations for each of your test problems. Now, some of those test problems did not require StatCrunch, did it? Okay, so I'll be looking for the .scs file backing up your answers that you gave WebAssign in your assignments test, and I'll be able to check your StatCrunch solutions as well. Okay, do you all see that? Okay, we're down to Isabella and Shalov. Okay, I'll announce this when I post the exam tomorrow, that there will be a requirement to submit your .scs file after you've completed your final exam. Then you'll send me separately the .scs file. Okay, guys, that's it on the review. Are there any? Let's see if there was. I think there was a question here. What time will I post the test tomorrow? As early as possible. Okay. Sometimes things come up and I don't get it posted until later in the day, but I think I'll be able to post it before noon tomorrow. Okay. All right, guys, I'll end it there unless you have any other questions. Any questions before we end? Okay, good luck. And I will have an office hour tomorrow at 11:30. So if you have any questions, just log in and I'll be there. Okay. All right. Bye now.
Thank you.
Thank you.